I am Professor J. N. Mandal, Department of Civil Engineering, IIT Bombay. I will teach you today about the seam strength of the geotextile material, because sometimes you require to connect one geotextile with another geotextile. You require sometimes teaching, you require sometimes seaming, you require sometimes welding of the geosynthetics material. So this is very important because this is the joining between the two defined types of the either woven or non-woven geotextile, or it may be the geogrid material. Therefore, one should know the seam strength of geotextile. Now, seam strength of geotextile is as per the specification ASTM D4884 and International Standard Organization ISO 13426. The main objective of this test to determine the seam strength of the geosynthetics material. So, maximum resistance of the junction formed due to the joining of two geosynthetics is called the seam strength. You can see here different types of the joining system, and this is the butter seam type, that is SSD2, and it is like one geosynthetics material here, another is geosynthetics material here, and then you are teaching at the spacing of 25 millimeter, and this is called butterfly seam. This is another kind of the joining which you call J type of seaming. So, this is J seam type SSM2, and this spacing between the two joining is about 25 millimeter. And this is another type of joining which is called flat or pair seam type of, this is SSA2. So, here also these 25 and 45 millimeter. So, what I will recommend that butterfly of the system is recommended for the joining. Now, the test is performed the same that in universal testing machine and strain rate about 10 to 3%. It is the same as we perform the tensile strength of the geosynthetic material, and clamp arrangement is the same. The slightly difference in the sample size, as you know, in case of tensile strength of the geosynthetics, the size is about 100 millimeter by the 200 millimeter, but in this case this two geosynthetic material is teaching here. So, it is seaming here it is. So, it is about 25 millimeter and 25 millimeter projected, and this is the teaching, and then you perform the tensile strength of the geosynthetics material. So, procedure: mount the specimen centrally in the camp, start the tensile testing machine and the area measuring device, and as I said, the strain rate is 10 plus minus 3% per minute, and the unit of the seam strength in terms of the kilonewton per meter. So, tensile strength is directly measured from the instrument as maximum force per unit width to cause the rupture. I also told that butterfly seam is recommended for the seam. So, how to calculate the seam strength? So, seam strength can be calculated, and seam strength efficiency can be expressed as AC is equal to T seam divided by Tg into 100. What T seam is the wide wedge seam strength as per ASTM D4884, and Tg is equal tensile strength without steam. So, one is without steam, another is with steam. So, you take the ratio of T seam and the Tg into 100, and which will give you what will be the efficiency of the geosynthetics material. And this seam strength you have to take into consideration into the design. Now, specimen calculation for what the tensile stress, let us take type of the material, it may be geosynthetics or the geomembrane material, and type of the second stream is maybe the fusion, or tensile strength without stream is 39.4 kilonewton per meter, and with stream strength is 35.4 kilonewton per meter. So, you can determine what is the stream efficiency. So, stream efficiency AC is equal to T stream divided by Tg into 100, that means 35.4 divided by 39.4 into 100. So, this efficiency is 89.84 percentage. So, this one should understand that what will be the stream strength of the geosynthetics, because this is one of the weakest point of the geosynthetics material, and that you have to consider into the design. Otherwise, sometimes that infrastructure or any kind of the design, there will be a possibility for the failure of the geosynthetics material. Next, I will discuss the hydraulic property. So far what we have discussed, this is all strength related problem where you use the geosynthetics material for the design of the reinforced soil retaining wall or the slope related problem or pavement related problem. Now we will discuss the another property, so it is hydraulics property. It is very important, and hydraulic property is related with the flow related problem. It may be flow of liquid or the water or the gas. So this is also very important. It should be related with also the drainage and also the filtration system. So this hydraulic property, we have to determine what will be the porosity of the geosynthetic, what will be the apparent opening size or the equivalent opening size of the geosynthetic material, percentage open area, and the permittivity of the geosynthetic material and transmittivity of the geosynthetic material. These are the two parameters is very important, particularly the permittivity and transmittivity, and also the equally important that what will be the apparent opening size or equivalent opening size of the geosynthetic material. So I will just proceed one by one how you will perform all the kind of the testing. That is, first that permittivity of cross plane permeability, and this test is performed as per ASTM DIP 4491 and ISO 11058. The main objective of this test to determine the permittivity of a geosynthetic material. Now, what do you mean by the permittivity? So, permittivity of the geosynthetics is defined the discharge of the water per unit cross sectional area per unit head under the laminar flow condition. And main function of the geosynthetics is the filtration when the water flow perpendicular to the geosynthetic material, not across the geosynthetic material. So, you remember that when you talk about the permittivity, then water is flowing across the plane of the geosynthetic material. So, that what you call the permittivity, and you have to determine whether it is a permittivity or the transmittivity, whether it is a filtration or the drainage. You have to decide, and you have to apply accordingly to your particular problem or particular application. Now, this test is performed with the constant head test or the falling head test method. So, I will show you what is the constant head method and the falling head test method. So, here you can see that this is the geosynthetic material and the water is flowing from the top to the bottom. This is Q in and this is Q out, and this is the geotextile material, and this geotextile material has a thickness, that is T of G, and this is the thickness of geosynthetic material, and water is flowing across the plane of the geosynthetics. So, you know that for the permittivity of the geosynthetic material from the Darcy's equation, I can write that from the Darcy's equation, that is, you know, Q is equal to K into N into I into A into G. So, this again is equal to K into N, I is equal to delta of H, and Tg is the thickness of the geosynthetic material, and A is equal to area of geosynthetics. So, you can write K of N divided by T of G is equal to Q divided by delta H into A of G. So, this is the psi is the permittivity. So, this you can say this part is the psi which is permittivity will be equal to Q divided by delta of H into A of G. So, psi which you call the permittivity, and this unit is per second. Remember, this units of permittivity is per second. Okay. Q is the flow rate is meter cube per second, and Kn is the hydraulic conductivity, that is the normal to the geosynthetic, that is unit is meter per second, and the delta H is equal to head loss, and Tg is the thickness of geosynthetic material, and A of G, the A of G is area of geosynthetic material, which you can say that L into W, that is in meter square. So, you know what will be the length of the geosynthetic material and what will be the width of the geosynthetic material. So, knowing this value of quantity of flow of water passing through the geotextile and the head loss and the area of the geosynthetic, that is length into the width. So, you can determine what is the permittivity, and permittivity unit of permittivity can be expressed as meter per second only. Now, this another also kind of the defined hydraulic gradient, you can write the defined hydraulic gradient of the hydraulic gradient, the flow rate of Q will be the different. The slope of the Q by Ag versus this is slope, this is the slope of Q by this is the slope defined hydraulic gradient you are taking, and this is the this is the different hydraulic gradient of flow rate, that is Q will be the defined types the slope of Q by A of G versus delta of H curve at the origin, which will give you that what will be the permittivity of the geosynthetic material. Now, what are the equipment you require for the determination of constant head permeability test of the geosynthetic material? So, you require that what is the stand pipe, and geosynthetics is climb, geosynthetic is climb here, and the device and discharge pipe, and then it is the reservoir. So, water can flow from top to the bottom at a constant head of permittivity, and then you are collecting the water here in the reservoir. So, after collecting the reservoir, it is another kind of falling head permeability test method. This is a geosynthetic material is here, and this distance is the initial time T0 when the height is initial Hi, and when the this is the time after a certain time, this time is T of F, final time. So, then this is the H of F height which we are measuring from here to here, and geotextile material is here. So, this is the stand pipe. So, from this test, so you can determine that what will be the permittivity of the geosynthetic material. Now, this procedure for constant head test, the apparatus is assembled and specimen is clamped, fill the apparatus with water until water overflow, adjust the discharge to obtain a head of about 50 millimeter. So, the test is performed under this head and record the quantity of water collected from the discharge pipe for a certain time interval and repeat the test as different head. So, permittivity is recorded as the average value from all the tests. So, you can calculate the permittivity. You know the equation psi is equal to Q by H into AT. So, where Q is equal to quantity of water, H is equal to head maintained, A is equal to cross section area of the specimen, and T is the time of flow. So, knowing this value, what will be the quantity of water you have collected at a particular time. So, what will be the height, you know what the head, and you know the cross sectional area of the geosynthetic material. So, you can determine the permittivity using this equation. Now, another procedure is the falling head test method. This apparatus is assembled and the specimen is clamped and fill the apparatus with water until the water overflow. So, adjust a water level in the stand pipe and then you can start the stopwatch and note the time for a fall of about 20 millimeter in the level of the water in the stand pipe. So, record the minimum 5 reading. So, you can use this equation that is equal to psi, which you call the permittivity. So, equation you know psi is equal to 2.3 into A divided by A of G into delta of T into log of 10 H of I by H of F. So, you know this I pi which you call the permittivity, and the unit is per second, and a small a is equal to area of stand pipe, you know area of that is stand pipe, okay, that is let us say meter square, and Ag you know area of geosynthetic material, area of geosynthetic material, and this is in meter square, and Hi is equal to initial head at time t0, and H of F is equal to final head at time t of F, and delta of t is equal to that is t of that H of t at a particular t of F and t of 0, that is change in time, and that is which unit is second. So, knowing this all these value, you know cross sectional area of the stand pipe, you know what will be the H1 value and the HA value, and you know the what will be the delta of T value, you know what will be the area of the geosynthetic material. So, you can calculate the permittivity of the geosynthetic material. So, specimen calculation for the to determine the permittivity of a specimen. For example, you are taking that type of geosynthetics is the non-woven geosynthetic material, and quantity of water collected is about 204.95 millimeter cube per second, and the head maintenance about 50 millimeter, and cross section area of the sample is given 2.827 millimeter square. So, you know the equation, permittivity is equal to Q by delta H into A. So, Q is the quantity of water collected, that is 204.95, this divided by, that is delta of H, that means head measurement is 50, and this into, this is cross sectional area of the sample, this is 2.827. So, if you can calculate, so you can obtain the permittivity, which is 1.44 per second. So, this is what we call the permittivity of the geosynthetic material. The permittivity of the geosynthetic material is very important, and particularly in case of the drainage and the filtration problem. And you remember permittivity, then when the water or gas pass across the plane of the geosynthetic material, and the unit of permittivity is per second. Now, we will discuss about the transmittivity of the geosynthetic material. Now, transmittivity, it is in plane, then when the water or liquid or gas pass along the plane of the geosynthetic material is called the transmittivity. So, this transmittivity can be done by the ASTM D4716 and ISO 12958. So, main objective of this test to determine transmittivity of a geosynthetic material. So, transmittivity of the geotextile is defined as the discharge of water per unit width per unit gradient in the direction of parallel to the plane of the specimen. The major function of the geosynthetics is the drainage when the water flow along the plane of the geosynthetic material. So, you remember between the difference between the two, one is the filtration, another is the drainage. In case of the permittivity, it is a filtration, and in case of the transmittivity, it is a drainage. That means, when the water flow along the plane of the geosynthetic material. So, how to that calculate that transmittivity? So, from the Darcy's equation, you know Q is equal to K of P into I into A of G. So, this is K of P into I into, here area is equal to W of G into T of G. So, we can write Kp into T of G is equal to Q divided by W of G, this into I, or Kp by Tg, which you call the transmissivity, and this is expressed as theta, and this is transmittivity, this unit is meter square per second. So, here because water is flowing along the plane of the geosynthetic material, that is why this, if the geosynthetic material is like this and water is flowing along the plane of the geosynthetic material. So, this geosynthetic material has a certain thickness, that is T of G, and this width is equal to this W G, width of the geosynthetic. That is why this area, because it is flowing along the plane of the geosynthetic material. So, that area of geosynthesis will be W G into T of G. So, what you know that theta, transmittivity of the geosynthesis material, the unit is meter square per spring, meter square per second, and Q is the flow rate, that is meter cube per second, and Kp is the hydraulic conductivity in plane of the geosynthesis material, and I is equal to hydraulic gradient, that I is equal to hydraulic gradient is equal to delta H by L of G, and delta H is the what you call head loss, and Lg you know length of the geosynthesis material, if this is the length of the geosynthesis material here, and Wg is the width of the geosynthetic material, and Tg is the thickness. So, you know all these value, so you can determine what will be the hydraulic conductivity or the transmittivity of the geosynthetic material. Now, from this you can different types of the hydraulic gradient you can take, and the flow rate Q will be the different. So, slope of the Q by Wg versus the I curve at the origin give the permittivity. So, there are different types of the test. One is the full length in plane flow, another is radial in plane flow. So, full length in plane flow you require the accessory, that what will be the metal base, what will be the reservoir, what will be the loading mechanism, and outflow weir and the manometer. So, here you can see that this is the equipment and this is the geosynthesis material, which is located between the two solid plate, and the water reservoir is here. Water is flowing across the plane of the geosynthesis material, and you are collecting the water here in a container, and then you will be knowing what is the quantity of water passes along the plane of the geosynthetic material and collected into this water jar, and at a particular time what will be the volume of water collected here, and the difference in the head is equal to delta of H. So, this is you have to perform the test under different loading. It may be the 50 kilonewton, 250 100 kilonewton, 250 kilonewton, or the 300 kilonewton or 350 kilonewton, or 400 or 500, 600, 700, 800, and then you can correlate between the what should be the quantity of water processed and what should be the load. So, you can draw a correlationship between the quantity of water flow and then what should be the applied load. So, you know each and every time what will be the quantity of water flow and what will be the under what pressure. So, you can make a correlation between the applied load and corresponding the quantity of water. You can have a nature of the curve, the quantity of flow is load is increasing, your quantity of water flow is decreasing. So, this is very important when you will use that PVD or prefabricated vertical drain for a particular project. This is very important, what quantity of water should flow through the geosynthetic material. Thank you.